everybody. In the last class, we had looked at adder subtractor circuit. We defined half adder, we defined full addition, and then we looked at 4-bit addition, even 8-bit addition, and there we had seen ripple carry addition. So, in today's class, we shall look at how the propagation, what is the propagation delay in ripple carry adder, how it is calculated, and then we shall look at some circuit which is which gives us fast addition. I mean, where the addition is done in quicker time. So, addition is done means subtraction is also done when we talk about 2's complement arithmetic. Okay. So, we begin with what is the delay in ripple carry addition, right. So, if you remember the example where in 4-bit addition 1 1 1 1, that is A, was added with B 0 0 0 1. We found the carry that was generated in the first stage, right, that ripples through the subsequent stages to come to arrive at the final carry. So, 1 1 1 1 when it was added with 0 0 0 1. So, carry generated here. So, this carry is finally coming to the final stage. So, that is why it is called ripple carry. Okay. So, if we place the numbers at a time say t is equal to 0, okay, and we assume that each of the basic gate delay has a propagation delay of tau, minor variation can be there, it is approximately tau for each one of them, right. And of course, we take note of that XOR gate requires a b prime a plus a prime b, that kind of circuit which requires 2 tau gate delay, that is the 2 basic gate delays if you consider the way it is arranged. So, if that is the case, then how much is the delay in completing the ripple carry addition for 4-bit. Okay. So, the maximum delay path, the critical path that we shall see. So, that is when the number is placed and we have to wait for the carry to arrive at the endmost adder. Okay. So, that is the time that we will consider, right. So, t is equal to 0 and we have noted that the carry is generated by a b plus b c in plus a c in. So, that is one bank of AND gate and there is a OR gate. So, 2 tau delay is there to generate the first carry C naught, right. So, this will go over here, right, and then again a AND operation and OR operation will take place. So, another 2 tau. So, C 1 will require another 2 tau, that is 4 tau, C 2 6 tau and C 3 finally it will require 8 tau. Okay. So, if it is 8-bit it will require 16 tau. So, we see the propagation delay here is cumulative, and for n-bit addition 2 n tau delay will be there, okay, for the generation of the carry. And let us see what is happening for the sum bit generation. So, we consider say S 3. So, S 3 will be A XOR B I, right. So, this XOR first part is done in 2 tau time, right, the XOR gate delay is 2 tau. Okay. And C 3, C 2 is available at 6 tau. So, after that another XOR operation is required. So, this 6 tau and 2 tau together 8 tau will be the time after which S 3 is also available. Okay. So, that is the maximum time it is required. So, others are available little earlier, okay. But if you consider as a whole, this 4-bit addition will require 8 tau amount of time, okay, in maximum case, okay, when carry is there at the endmost point. Okay. Now, we said that we would look at some mechanism by which this addition this time can be reduced, right, because we have seen if the number of bits are more, then the delay is getting accumulated. I mean, if it is n, it is 2 n tau, that kind of thing. So, one way of doing thing is to investigate the carry generation equation, and if we look at it. So, this is the basic carry generation equation, right, and we see that there is a recursive kind of activity within the equation. So, C I generation is waiting for C I minus 1, C I minus will wait for C I minus 2, C I minus 2 will wait for C I minus 3. So, there is it is happening in cascade serially one after another, and because of which the delay is getting accumulated. Okay. So, the method that we shall try is to make this process parallel instead of serial. Let us see how we can do it. So, to do that we are defining two terms. So, first of all we are writing C I as A I B I, and the C I minus 1 we are taking common A I plus B I, and then we are writing in this way. Okay. So, it is easier to for notation purposes also. Every time we do not need to write two variable. So, one is G I, which is A I B I, another is P I, which is A I plus B I. Okay. One is obtained by AND gate after one gate basic gate delay, another is obtained by OR gate to input OR gate after again one basic gate delay. Now, the first one is called generation term, okay, and the second one is called propagation term. Why are they called so? Generation term, if G I is 1, then carry will be generated at that stage. It does not matter whether a carry was there in the previous stage or not. Okay. If both A and B are 1, A I and B I are 1, so C I will be 1. It does not really matter whether previous stage is generating any carry or not. So, that is why it is called generation term. And what is the propagation term P I? What is its significance? If P I is 0, whether P I is 0 or not, we can figure it out from this stage itself. If P I is 0, then even if the carry is there in the previous stage, it will not get propagated, because C I is at minus 1 is ANDed with P I. Okay. So, only if P I is 1, propagation term is 1, and if there is a carry in the previous stage, then that will contribute to generation of the carry in this stage. So, that is why it is called propagation term, right. So, this is the significance of it. Now, with this G I and P I, right, we try to revisit the equation. So, C naught is G naught plus P naught C minus 1. C minus 1 is the first stage. So, if from the previous stage if it is there, or if it is the very first stage, it will be 0. Okay. Otherwise, if it is in cascade, so something will come from the previous stage, right. And C 1 is G 1 plus P 1 C naught, the basic equation, this equation only, this equation we are employing. So, this C naught, okay, we can substitute from equation 1 in equation 2. So, that is what we are doing here. So, if you do that, what will happen? C 1 is G 1 plus P 1 G naught plus P 1 P naught C minus 1. This is what we have got, and by this what have we achieved in terms of delay? So, G I and P I generation 1 tau, it is there. So, this is one AND gate, this is one AND gate, 2 input and 3 input AND gates. So, they are generating output in 1 tau, and finally, this is ORed, that is 1 tau. So, 3 tau, after 3 tau we get the value of C 1. Earlier using ripple carry mode, what was the time required for C 1? It was 4 tau. Okay. So, there is some benefit. Whether this benefit is there for larger number of bit addition, so 3 bit, 4 bit, let us see in the next slide. Okay. So, for that we investigate the basic equation of C 2. C 2 is G 2 plus P 2 C 1, that is the basic equation, the recursive equation C 1. Okay. So, C 1 we substitute from the previous equation as G 1 plus P 1 G naught plus P 1 P naught C minus 1. Then we expand it. Okay. So, again what we see that each of these pi and gi's are generated after 1 tau. Each of these AND gate, which is doing a parallel operation, will take 1 tau. Okay. So, 2 tau and final 1 OR gate to combine all these product terms, right. So, another tau. So, it is obtained after 3 tau delay. So, even for 3 bit addition, it is 3 tau, that is generated after 3 tau. Okay. And C3 for 4 bit operation, again basic equation is G3 P3 plus P3 C2. C2 we can substitute from equation 5 here, and again we will get a equation similar to this. There also we can see that Gi Pi terms will generate in 1 tau, and these product terms another tau, and final 1 OR terms, it is total 3 tau. So, irrespective of the number of bits, we can see that the time required to generate the carry here is 3 tau by this bringing this kind of parallelism instead of the serial mode of carry generation that we had seen before. Now, one need to be careful about the how many gate it is getting connected to, the fan in fan out issues. So, as long as that is not violated, it is able to provide as much of current or sink current. So, there is no issue. Okay. But that is something for which we cannot indefinitely extend it. Okay. We have to confine it to certain number of bits. Okay. So, now then that is the way the carry is getting generated. So, carry is generated after 3 tau, right. And what about the sum bit? So, A XOR Bi, that is already available through XOR gate in 2 tau, and the carry we are waiting for the carry to come, which is 3 tau for say 4 bit addition or so, I mean which is the same. So, 3 tau and 2 tau together, after 5 tau we are getting the final result, okay, maximum 5 tau. Earlier it was, you have seen that it is 8 tau. So, and in this case the delay is not cumulative. And how we realize this circuit? Okay. So, the circuit realization is a little bit more complex than what was in case of this normal ripple carry addition. So, we are showing 2 such bits here, 2 such sum bits, that is on carry bits, that is getting generated. So, this is your A1 B1 and this is A0 B0, and this is G1 P1 and G0 P0 are getting generated by AND gate and OR gate, AND gate and OR gate. Okay. And then the C0 will require G0 and plus P0 C minus 1, right. So, this is the G0 is coming over here, this is ORed with P0 and C minus 1. So, this is another input of the OR gate. Okay. So, this is how the C0 is getting generated. Okay. And what about C1? C1 will be G1 plus P1 G0 plus P1 P0 C minus 1. So, G1, right, and then your P1 G0, this is your P1 G0, and then P1 P0 C minus 1, this is P1 P0 C minus 1. Okay. So, that is how C1 is getting generated. Now, regarding the sum bits that is to be generated, we can generate from A XOR B. Also, you can calculate and you can see that G XOR P XOR Ci is also giving you the same output. Okay. So, it is preferred that we generate it from G XOR Pi instead of A XOR Pi, because it is connected to the external world. So, how it will load and other things, that is not much known to us, how it is getting driven in the external circuitry. So, here we know how much current it can handle and other things. So, when we generate the final sum bit, we take the XORing from GIs and PIs instead of AIs and AI and BI. Okay. So, this is a commercial IC, IC 7483 A. You can search and you can see there are other ICs also 74283 and where which does 4 bit fast addition, and here this is different manufacturers has got different way of representing the number. So, here these A0, A1, A2, A3 that is mentioned, B0, B1, B2, B3 is mentioned, output is S 0 to S 3, the same nomenclature we have followed, but input we have used C minus 1 and C 3, the final output carry output they are using C 0 and C 4. Okay. So, one value more. So, in some other manufacturer you will see instead of the sum bit they are using the sigma sign, summation sign, 1, summation 2 and so on and so forth. So, these are certain small differences that you have to take note when you are using it practically in lab or in your personal hobby project or mini projects, digital electronics project. The other thing that you take note of is the use of NOR gate, NAND gate and here again NOR gate, okay, instead of the kind of thing and or that we have used. Okay. So, for which again if you work it out, then we will see the same logic. We shall see one example at the end, okay, for a carry look at a circuit, okay, group carry generation in relation to that particular discussion. So, this is something we take note of when we use this kind of IC. Now, these are 4-bit first adder and we need 8-bit addition. So, how we go about it? Now, here again we shall be using cascading, right. So, this cascading, for cascading we shall be using one adder and this is another adder. Now, in between how we are connecting, the output carry that is generated here is going as input carry. So, this is nothing but the mode which is similar to ripple carry addition, is not it. So, this carry input 13 here, carry input of the more significant bits will be waiting for the C 3 to get generated from the previous stage, okay, which will require 3 tau. So, if you have got another such stage here after this, so this is 4 bit, this is 4 bit, so this is another say 4 bit over here. So, it will wait for 6 tau to generate this particular carry, right. So, that way this becomes within the across stages, across these 4 bit blocks, the carry ripples from one IC to another. So, that becomes cumulative. Within this block it is not, when we are looking for this kind of arrangement. Is it okay? Is it understood? Okay. But each of this block is a first adder, the kind of addition that we have seen before, okay, which is called carry look ahead adder. And here again we are showing the arrangement of getting both addition and subtraction using first adder, and for that we are using the similar approach that we had done before. So, we are having a bank of XOR gate here and a bank of XOR gate here, and the sub input is 1 when we are doing subtraction, and which adds to the carry, initial carry in the 2's complement of this B7 to B0 number. So, this is 1's complement at the XOR gate output and 1 that is getting as input carry over here, okay, right. And when it is addition, this sub will be 0. So, basically only B not to B7 will come over here, okay, no inversion will be done, and this is 0. So, this is normal addition that will take place. Okay. So, we take note that within the across these blocks it is carry is rippling. Now, we look at a mechanism, a method by which that particular aspect can be addressed. Okay. If we have got first addition in our mind, right, and we are having a situation where more than 4 bit addition is required, okay, say maybe 12 bit, 16 bit or so. So, how we can what we can do to speed it up. So, to do that let us again look at the basic equation of the carry generation. So, the carry that is C 3 is going as input to the next block that we had seen. So, we are looking at this C 3. Okay. So, how C 3 is getting generated? So, this is the way C 3 is getting generated in the first carry first adder. Okay. So, this term this term, okay, if when it is 1, this C3 is getting generated irrespective of there was a carry to the input to this block or not. Okay. So, this we define as group carry generation term, group carry generation term G3 to 0. Okay. Is it clear? And this particular term in a different color, okay, when this is 0, then even if there is a carry present at the input of this block, this will not get propagated. It is similar, exactly similar. You will see the equation and other things that we will get is exactly identical to the one that we had seen in case of first adder development, isn't it? So, this we say group carry, because it is generated from individual AIs and BIs, these proportion term, okay, the ordering of AIs and BIs at individual bitwise ordering. So, this is the group carry propagation term, right. So, now we are looking at this as a group. So, this is 4-bit adder, first adder. So, this is your C3 and this is C minus 1 and this is C3, okay. And this were your A320 and this is your B320. Okay. So, how what you can write now? Now that we have defined them. So, C3 is equal to G320 P320 C minus 1. It is similar to the equation that we had seen before, if you remember. Okay. So, this is the kind of equation that we had seen before. So, earlier we are doing it bitwise carry generation, now it is blockwise carry generation, right. So, this is what we are doing it, and this is the group carry generation term and group carry propagation term. Earlier it was only generation term and propagation term, here group generation term and group carry propagation term. That was bitwise, this is blockwise. Okay. This is the difference, clear. Now, if there is another block after this which takes C3 input and generates C7. Okay. So, this C7 can be written from the generation terms and propagation term that is generated at that particular block G724 and P724 and with input as C3. This is just similar thing, right. For the next particular block we can write it in this manner. Now, this C3 we can substitute from the previous equation over here and then expand it, that is what we will get. This is similar again identical to the treatment that we had when we developed first adder. Okay. So, that way we can go on doing it for the next stage and the next stage and all. So, for 16-bit addition, so C15 is getting generated in this manner, right. Now, each of these term, if you look at them, so that if you are generating them at each of these output, if you are additionally you are generating this group carry generation term G320 and P320, each one of them if you are generating, and if you are making use of them to generate the say C15, then how much time is required? So, this G320, this will require 3 tau. Why? Each of these GIs and PIs is requiring 1 tau. This product term is another tau and the final ordering is another tau. So, GI, each of these group carry generation term will require 3 tau and group carry propagation term will require 2 tau. Okay. So, the term here, these are 2 tau, 3 tau and these are 2 tau. This is 3 tau, each, I mean while for their generation. So, the higher of these 2 is 3 tau, okay. And this 3 tau and then there is a product 1 tau and then finally is another ordering. So, this is the after 5 tau you are getting this particular carry here. this particular carry here. Okay. So, we need to have an aggregator to, and each of these term need to generate this group carry generation, group carry propagation term. And we see that the equation is similar. This aggregator can also take individual bits also to generate the corresponding carries at individual level, the carries. Okay. This is what we can understand by comparing the equations. So, this is one circuit for look ahead carry generator IC 74182. Okay. And this particular one takes 4 such terms, okay, 4 generation term and 4 propagation terms. So, this could be group carry generation term and group carry propagation term as well, or normal basic numbers. Okay. Then the corresponding these because the basic equation remains the same, the way we have seen it before. Okay. And this is the input carry, and these are the output carry for individual stages, and this is the final again group generation term and propagation term for multi-level use, next level use. Okay. And this is the corresponding circuit, and we told that again we are having inverter, then NOR gates and other things, which may make us think like the example that I had given before. So, for example, this circuit. So, let us investigate one such particular block and see whether it matches with the equation or not. Okay. So, this is the block that we look at. So, this output over here is, the input here is G naught bar and P naught bar, that is getting ANDed, right, and this input is G naught bar is coming from here, and Cn here is active high, but then there is an inverter. So, this is Cn bar. So, input to this NOR gate is G naught bar, P naught bar and G naught bar, Cn bar. Okay. So, input to the NOR gate, which is generating Cn plus x. Okay. The first level carry is is this one. Okay. Then you apply this De Morgan's theorem, right. So, this G naught bar, P naught bar, the whole bar ANDed with, because this odd sign is becoming this AND term, and each one of this term is inverted, complemented. So, G naught prime, C naught prime and this bar. Then you again perform De Morgan's theorem. Okay. So, this becomes G naught complement of complement, that is G naught, and P naught complement of complement, that is P naught. Similarly, this is G naught and this is Cn. Okay. Right, you can follow it. Then when you perform the product, get each of finally in a sum of product form. So, G naught, this gives you G naught. So, G naught Cn, G naught P naught and P naught Cn. And if you take common G naught, then 1 plus 1 odd Cn odd P naught, which is nothing but G naught and P naught Cn. So, you get back the basic equation G naught plus P naught Cn here is C minus 1, the one that we have used that concept. So, this becomes your C1, and if it is group carry, these are the group carry terms, this is G3 to 0 plus P3 to 0, and this is C minus 1, this is your C3. Okay. Have you understood it? And similarly, for other terms, depending on whether it is group carry or normal generation propagation term, it will generate for that particular bit or for that particular block. Okay. So, with this we conclude today's class. Propagation delay is cumulative in a ripple carry adder. If basic gate delay is tau, if we consider that as tau, then n bit addition is done in 2n tau time, since the placement of valid data. Carry look ahead adder does a serial to parallel conversion internal process for optical carry, by which the addition is completed in 5 tau time. Please remember, this is 5 tau time within the block. Okay. cascading parallel adders where carry output of one block is fed as carry input of the next block makes the carry ripple between blocks with cumulative delay. Okay. And to avoid that, we can have additional group carry generation and propagation terms, and by which we can get carry look ahead by a aggregator, and that reduces the time for generation of the carry. Okay. Thank you.